In this video I'm going to delve into the chemistry that underlies the greenhouse effect. I'm sure from GCSE that you have seen a picture like this many times, but let's just check we are clear with what's actually happening. So the sun is an incredibly hot body, no surprises there. It's radiating out energy, and that energy is very high frequency, and it has a very short wavelength. And so we are looking mainly at visible radiation and ultraviolet radiation. Some of that energy is absorbed by the atmosphere, very small amount, but most of it is absorbed by the Earth itself. Now, the Earth is a much cooler body. It is also radiating out electromagnetic radiation, but it's mainly in the form of infrared, the mid-infrared part of the spectrum in particular. So we are talking a lower frequency and a longer wavelength. And this is what we can see being indicated by these arrows here. Now, a good proportion of that energy is lost to space, but another good proportion is absorbed by molecules in the atmosphere. And this is the beginning of a chain of processes by which the atmosphere is warmed. How does this look in terms of the electromagnetic spectrum? How are all these frequencies of radiation related? Well, we can see here that ultraviolet and visible radiation, this is the radiation that's being emitted by the sun, and the Earth is emitting radiation in the mid part of the infrared part of the electromagnetic spectrum. What happens when molecules absorb radiation? Well, it depends entirely on the frequency or the wavelength of this radiation. So, for example, when molecules absorb very low frequency radiation, so radio waves for example, it causes our molecules to move around more. Technically, we say that there has been an increase in the translational energy of our molecules. When molecules absorb microwave radiation, it causes them to rotate or to spin faster. We say that there has been an increase in the molecule's rotational energy. And then, this is where we are most interested, molecules absorbing infrared radiation. This causes an increase in their vibrational energy. So we see that their bonds vibrate more strongly. I mean, to be very clear here with our language, we're not saying that they start to vibrate, but by absorbing infrared radiation, it causes the bonds to vibrate more strongly. So we see an increase in the molecule's vibrational energy. And as a result of this, we find our molecules, as their bonds start to vibrate, the molecules bump into their next door neighbours. The energy is converted into kinetic energy, and the atmosphere is warmed. Hopefully we'll be able to see that more clearly in this little diagram. So translational, so this is when molecules are absorbing very low frequency radiation. So we are talking about radio waves. Can I fit that in? Just about. And it causes our molecules literally just to move around more strongly, more energetically. When they absorb microwave radiation, then we get an increase in their rotational states. Molecules started to rotate more strongly. And then vibration, if we are absorbing infrared radiation, molecules start to vibrate more strongly, and there are a number of ways that we can do this. As you can see here, we get bending vibrations, symmetric stretching, asymmetric stretching. Now, molecules absorb specific frequencies of radiation. The exact frequency of infrared radiation it takes to make, say, a carbon dioxide molecule vibrate more strongly is going to be different to the amount of energy or the frequency of radiation it takes to make a water molecule vibrate more strongly. Why? Well, we have different strength bonds, is the quick answer. So bond strength is a key factor here. Indeed, we know that the energy levels in molecules are quantized. They're at fixed levels. So for a molecule to move from, say, vibrational level 1 to vibrational level 2 requires it to absorb a specific frequency of radiation. And you may be familiar with the expression delta E equals HV. So there's my frequency. That is the difference between the energy levels, difference between energy levels, and H stands for Planck's constant. Planck's constant. So this distance here is different depending on the molecule. How does that affect, or why is that relevant to trying to understand the greenhouse effect? This graph is showing us, for gases that are common in our atmosphere, the wavelengths of infrared radiation that they absorb. So if we look at water, for example, it will absorb this specific wavelength of radiation, and that will cause the bonds in the water molecule to vibrate more strongly. As a result, that water molecule will collide with neighbouring molecules, the energy will be transferred into kinetic energy, and the atmosphere becomes warmer. We can see that water, as, how am I going to show this here? Water, we can see here, if you look at the graph quite carefully, with the black lines, absorbs strongly between round about 2 to, should we say, 7-ish micrometers. The Earth is emitting infrared radiation in the wavelength range around 3 to 50 micrometers, just to give you some context here. We can see that carbon dioxide absorbs strongly at just after 4 micrometers, and also again in this range here, around about 14 to 16 micrometers. It's also important to notice that we've got methane as a greenhouse gas absorbing infrared radiation, but also gases that are not commonly thought of as greenhouse gases are all capable, and all do, absorb infrared radiation in our atmosphere. So carbon monoxide from the incomplete combustion of fossil fuels, nitrogen oxides, again from the combustion of fossil fuels, particularly in petrol and diesel engines, and ozone. Now we need to remember that ozone, as well as being in the ozone layer, is also a secondary pollutant. It's found in photochemical smog when primary pollutants from exhaust engines react together in sunlight. So all of these common gases in our atmosphere are absorbing infrared radiation, which leads the atmosphere to warm. And the greater the concentration of these gases in the atmosphere, the more infrared radiation that is going to be absorbed, and the warmer the atmosphere becomes. Now, we often talk about the global warming potential of a gas in the atmosphere, global warming potential, because a gas's particular effect on global warming is not just about which specific wavelengths or frequencies of radiation it absorbs. It's also about the gas's stability, i.e. how long does it last in the atmosphere. So gases that are not soluble in water are unlikely to be washed out, or gases that have very, very strong bonds, and I'm thinking about CFCs, for example, are very stable because they're not broken down by photodissociation. So there are many gases in our atmosphere that, although we have a very, very small amount of them, because they are there for a very long time, their global warming potential is actually quite high. Now, you may be aware of something called the IR window, the infrared window. If we plot the infrared absorption that's emitted from the Earth, so this is what we're looking at here. So this is infrared radiation emitted by planet Earth. We can see that water, as our most abundant greenhouse gas, absorbs most strongly round about these wavelengths, so that corresponds to water. Now there's a lot of water in the atmosphere, but all of this radiation emitted by the Earth is not absorbed by water, and it would escape to space. Now, in an ideal world, our atmosphere would not be warming because the amount of radiation absorbed by it pretty much balances out the amount of radiation that's emitted out to Earth. However, water vapour isn't the only gas in our atmosphere. We can see here, this corresponds approximately to methane. So methane's absorbing infrared radiation in that kind of region, and this corresponds to radiation absorbed by carbon dioxide. So gases or greenhouse gases that absorb infrared radiation that corresponds to the IR window are of particular concern because they are exponentially adding more and more warming to our atmosphere. In contrast, if we think about maybe gases like the nitrogen oxides that I talked about, carbon monoxide, other products of combustion engines, they absorb in the same region of the infrared spectrum as water does. So although we would have a greater abundance of gases in this window, they're not absorbing different frequencies. And then finally, we need to be aware of a positive feedback loop. Water, as the temperature of the Earth rises, more and more water is in the form of water vapour. And as a result of that, we have more water in the atmosphere, absorbing more infrared radiation, leading to a warming atmosphere and more water evaporating. We have a positive feedback loop. So the chemistry of greenhouse gases, of global warming, is very, very complex, which is why it's so difficult to model. However, I hope that gives you a better understanding of what's actually happening and how these molecules are contributing to the warming of our atmosphere. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the blurb below, it will take you straight to the Crunch Chemistry School, where you'll find all the resources you need to get that A-star grade at A-level. Together we can do this.